Hello, Algebra 2. Today we're going to be working on lesson 11.6, which is called recursive formulas. I'm going to chop this lesson down to its bare bones because it kind of expands out into zones that can be slightly difficult at times. So I'm just going to cut it down to its absolute minimalistic viewpoint and just do the basics, the absolute necessities. Now, things to come. Next lesson is about fractal patterns, which are reoccurring patterns. Instead of me doing a lesson and trying to guide you through the homework on that, I'm going to have you watch a NOVA video on fractals and answer some questions on things that you learned during the NOVA video. There are notes and there is a lesson in the book tied to it, but a lot of it is really hands-on. And so instead of me trying to do something that is maybe going to be a little bit confusing and there's going to be some loss in the teaching, I'm going to go ahead and show you the video that I would have shown you anyway. Either way, you would have watched the video. You just would have learned the lesson, done some of the stuff with me, and then watched the video. But instead, I'm going to let the video do most of the teaching for this particular lesson. And then we'll come back together and we'll try to get through lesson 8. Now again, lesson 8 I'm going to cut down to very bare bones because lesson 8 can be a lot to try to cover. And so I'm going to do some setup now for lesson 8 and lesson 6 because I'm going to have a little bit of extra time here. And then lesson 8 is not super difficult. It just it takes up a lot of space and it'll take a lot of time to try to convey. So hopefully everything will go well through the last 3 lessons of the chapter, and then I'll talk about it more when I'm filming lesson 8, but after we've done lessons 6, 7, and 8, we'll do the book review. I'll have a certain level requirement that you must complete, and then I'll have extra credit options, just like I always do for reviews. And then I'll be pushing out an exam, but like I said when we were all here, any tests you take won't be treated as tests. It'll probably be an old exam, not the actual exam I'd be using with you, and it'll be treated as some sort of worksheet so that you can work together and ask me questions if you want help on it, but it just needs to be completed. So that's what the end of chapter 11 looks like right now, and that's about as far out as I'm going to get for now until I have some more directive, because I've already pushed us out quite a bit of the way through the rest of the school year. Normally I would get through 11, 12, and the very first part of 13 before school's over, but with the reduced workload of distance learning, if I am making contact with you right now, that means I'm probably going to be making contact with you for a while, but none of us are really sure of that. But if that's the case, I think we'll be lucky to get through 12, and probably not even that before the school year ends. But we'll see how that pans out. Today's lesson is all about formulas that don't follow nice arithmetic or geometric patterns. So arithmetic sequences are plus sequences. So plus 2, plus 2, plus 2, plus 2, plus 3, plus 3, plus 3, plus 3. Geometric sequences are multiplier sequences. They have a nice multiplied pattern. Times 2, times 2, times 2, times 2, times 3, times 3, times 3, times 3, times a third, times a third, times a third, times a third. But these formulas that we're going to be working with today don't have that nice flow. Now, all of the ones I'm going to give you have formula entries, but some of the other patterns have more interconnected patterns. So rather than having a formula to just plug through, which all the ones you're going to do today are going to be just a formula that you continually plug through. It's like an endless loop of formula. Some of the patterns have more unique connectivity. So I want to talk about Fibonacci's sequence really quickly. This is probably something that we've discussed before, but it's probably been a really long time since we've discussed Fibonacci's sequence. So I'd like to bring it back up. Fibonacci's sequence is a connected sequence. In other words, each new term is dependent on the previous two terms. To get term 3, you add term 1 and term 2. 1 plus 1 is 2. To get term 4, you add terms 2 and 3. 1 plus 2 is 3. The prior two terms added together give you the next term. So the next term beyond what Mr. P's done in his sequence would be 8 plus 13 gives us 21. And then to go a term further, we would do 13 plus 21, which gives us 34. Now, these recursive formulas, these patterns, can be created into formulas, but the formulas are completely dependent on the fact that we know the prior terms. So Fibonacci's sequence can be written as AN, in other words, the next term, equals AN minus 1, which would be the previous term, plus AN minus 2, which would be the term before that. Now these formulas they're really difficult to kind of wrap your mind around, and a lot of kids get really caught up in this n minus 1, n minus 2 junk, which really isn't important at all. The n minus 1, n minus 2 stuff is just telling me go back one term, go back two terms in my sequence. But because it can cause a lot of student confusion, I'm not going to focus on any formulas that are dependent on prior terms like this particular sequence is. I just wanted to give you an example of what that would look like for those of you who might be moving forward in math and will be eventually dealing with sequences like this. I wanted to give you kind of a picture of what that looked like. And you might also see something like this in the video that you're going to watch. So I wanted to give you a picture of what that could look like. Now over here, Mr. P has begun a picture of Pascal's triangle. You can find Pascal's triangle, images of Pascal's triangle on the internet, anywhere you want them. And Mr. P has a Pascal triangle in our chapter notes that you can access as well. I'm not sure what lesson it's in. It's probably in lesson 8, but it could be found in lesson 6, 7, or 8. So I would check them. It could be in 7, just as likely as 8, but it's probably in 8 because that's where we're going to really, really heavily use it. And that's the reason I'm setting it up, is because I need to have a way to show you Pascal's triangle before I go do lesson 8, because lesson 8 is going to heavily use Pascal's triangle, and I don't want to be setting it up. The key to Pascal's triangle is to add diagonally above to get the new terms. So on the outsides I have 1s. In the middle of these two terms, I will have the addition of those terms. So 1 plus 4 is 5. In the middle of these two terms, I will have the sum of those terms. So 4 plus 6 is 10. In the middle of these two terms, I'll have the sum of those terms, which is 10. In the middle of these two terms, I'll have the sum of those terms, which is 5. You'll notice that Pascal's triangle creates a mirroring effect. If the row has an odd number of values, it will come into the center, pivot, and go back out the same way as it came in. 1, 4, 6, 4, 1. If it is an even number of terms, it will have a direct mirror on the left terms and the right terms. 1, 5, 10, 10, 5, 1. Now when we drop down to the next row of Pascal's triangle, and it's important to understand when we talk about rows of Pascal's triangle, moving forward, because we're going to talk about rows of Pascal's triangle, this row is considered row 0. This row is considered row 1. This row is considered row 2. The major indicator is that you will find the number in the row. So row 3 has the number 3, row 4 has the number 4, row 5 has the number 5, row 6 will have the number 6, etc. So when you're going to find a specific row, you're not going to start with this one. This one is row 0, and you're going to look for the number indicator. Okay, so when you're typing them in, if you want the 11th row of Pascal's triangle, it should actually give you the row with 11 in it. Now, some internet searches may screw that up, so you may have to go one row beyond. If you want the row with 11 in it, you may have to say the 12th row, depending on how the internet search goes. But that's, that's because somebody put it in wrong. Okay, let's create the next row, Pascal's triangle. 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, 5 plus 1 is 6, 1, and I'm going to go one more row down to the 7th row for now. 1 plus 6 is 7, 6 plus 15 is 21, 15 and 20 makes 35, 20 and 15 makes 35, 15 and 6 makes 21, 6 and 1 makes 7, and 1. Now for examples in lesson 8, you're going to have to go much deeper than that. I believe they go down to like the 12th or 13th row. But for now, we're only going to build it down 7 rows, which is just fine. Now I want to focus on what the actual assignment for today will be, because all of this was set up for future assignments or for things that you're actually not going to work on, but things that were in the lesson. The real meat of today's lesson is setting you up with formulas that are recursive. So I'm going to work a recursive formula, fx equals 3x minus 4 when x0 equals 3. So here's how these work. It's fairly simple. We're going to take the initial number, which is this x0, and we're going to plug it into our formula for x. So I need to do f of 3, which is 3 times 3 minus 4. Hopefully everybody sees that okay. 3 times 3 is 9, minus 4 is 5. That gives me the first answer in my pattern. Now, when we talk about recursive formulas, what happens is each answer then becomes the new value we plug in. We will get that answer, and then that becomes the new value we plug in. And the way this works is just it's an infinite loop of find a new answer, plug the new answer in. Find the new answer, plug the new answer in. So the book asks us to find 3 terms to our recursive formulas when we're working through these. We only need to find 3 solutions through the formula. Our first solution was 5. That is the new number we're going to plug in for x. So when I go to find my next formula, I'm going to do f of 5 rather than f of 3. But my formula is the same. 3 times 5 minus 4. All I do is I put this new answer back into x in the formula. 3 times 5 is 15 minus 4 gives me 11. 11 is my second answer. Now to go get my third answer, I'm going to take that 11 that I just got as my second answer, and I'm going to put it in the same formula to find its solution. 3 times 11 is 33, minus 4 is 29. Now I have already found my three solutions, 5, 11, 29. The original thing we plug in does not count as an answer. You did not find that. It was given to you in the problem. That does not count as an answer. 5, 11, 29 is your solution to this particular example. Alright, so now I'm going to jump down to the homework. This is exactly how the homework works, by the way. So if you head over to the homework page, which is on page 686, we're going to be working the problems in the zone 17 to 22. Please do not focus on the problems prior to 17 or the problems after 22. They are all things like Fibonacci sequence, which we're not going to worry about. I showed you an example of how they kind of work, but I don't want you digging in and stressing out over how to actually work through them. Okay? I am going to work one of these problems with you so you have another example, and that's problem 21. Problem 21 gives us fx equals 3x squared minus 4 with x0 being 1. This is the initial thing we're going to plug in for x in the formula that they've given us. So my first solution will be f of 1, which is 3 times 1 squared minus 4. 1 squared is 1. Times 3 is 3. Minus 4 is negative 1. The first answer to my problem is negative 1. Now I'm going to take that new answer and I'm going to plug it back into my formula. F of negative 1 equals 3 times negative 1 squared minus 4. Negative 1 squared is 1. 1 times 3 is 3. Minus 4 is negative 1. My new answer is also negative 1. I'm going to take that new negative 1 answer and I'm going to plug it back into the formula to find what my next solution is. Now obviously, for those of you who are following along, the answer is clearly going to be negative 1 again, right? Because it's the same formula, same process. I just found the answer, and so I have negative 1 squared, which is 1, times 3 is 3, minus 4 is negative 1. And that does happen sometimes. Sometimes you see a pattern in your solutions, like this one. Sometimes you do not see a pattern in your solutions, like this one. This one is just going to continue to grow larger and larger. This one is just going to be negative 1 all the time. Negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. And both are excellent examples of recursive formulas. They both work perfectly. Make sure you're finding me 3 full answers. You're running your new answer through, running your new answer through, running your new answer through, right? Make sure that you are prepared to watch the video for lesson 7 rather than actually doing lesson 7, and answer questions from that video on lesson 7. Then I will be back re-videotaping myself for lesson 8. After lesson 8, we'll be going into a review and test cycle, which means that I'm not going to have any direct video contact with you for a while. But remember, you still have assignments and things that you have to get to me. You can still Zoom conference with me. There's still, you can still email me. You can still get on the discussion board. I still need to have contact with you so that I can get my attendance in. Have a really great day, guys.